Welcome viewers, I hope all is well.
Feel pretty good, actually.
In this video, we're gonna do linear regression, and we're also gonna split the data into train and test sets. So let's start. I've already imported most of the libraries we're gonna need. So now let's read the file that we're gonna perform the linear regression on. pd.read_csv. And the name of our CSV file is score5.csv. Let's run this to see our CSV data, and you see our hours and scores column. So a great way to explore relationships between variables is through scatter plots. And we're gonna make a scatter plot using the Seaborn library. Scatter plot. And on our x-axis, we'll put the hours. On our y-axis, we'll put the score. And it's our data frame. Let's run this. And you see we plotted our hours and scores. Let's display the correlation between the numerical variables. And we'll do this with the Seaborn heat map. And we're gonna set the annotation to true because we want to see the actual value. Let me remove this because I just don't like it. plc.show. And you see hours and scores has a correlation of 0.98. Hours and hours will obviously have a one-to-one relationship because it's the same values. So now before we start with linear regression, let's put our hours and scores column into x and y variables. So we're gonna set x equals to our hours column. And we want the values. And we also have to reshape. And we're gonna do -1 and 1. So skyscalearn is not able to decide what we have passed is one row of data with multiple columns or multiple rows of data with a single column. So what this -1 means is to detect the number of rows automatically, and this one represents one column. So we have to do this for scikit-learn. If we don't, we will get an error. We could also do the same thing for y, but we don't have to, but I'm gonna do it anyway. .values.reshape. So now let's split our data using the train test split object. So first we're gonna create the x train, the x test, y train, and y test. And we're gonna set that equals to train test split. Then we're gonna put in our columns that we stored in our variables x and y. We're gonna set the test size to 20%. And this means that 20% of the data will go in our tests and the other 80% will be in the train. And this is what the 80% of the data in the train is what we'll use to train and fit our model. And then we need to set a random state and set that equals to 42 because the splitting is random by default. So when we set random state to 42, it doesn't randomize the data every time. Let's run this. Let's add a couple more cells. Let's look at our X train. And you see it's the 80% of our data. Let's look at the shape. And you see we have 20 rows and one column. And then our X test dot shape has the remaining 20% of the data. So now let's train our linear regression model, and we have to import our linear regression. So sklearn.linear model import linear, and R is a capital R, regression. Let's run this. You see everything is fine. So now let's fit our model. So we're gonna create our object, linear regression. Let's run this. Everything is fine. And now let's fit our data. So we're fitting the X train and the Y train. And let's run this.
You know, I was on a good run, and then boom.
Oh, it's a small y because we used a small y here. Let's run this. And we fit our regression line to our data. So now if we wanted to find the y-intercept, we simply print our model.intercept with an underscore. Let's run this, and you see we get our intercept. If we want to get our coefficient or slope, call our model and write coefficient. And you see we got our coefficient or the slope. So let's make predictions by creating a function. So we're gonna create a function called calc. Then we're gonna write slope hours and the intercept. And what we want these values to do, we want slope times our hours plus the intercept. So now let's make a variable called score, call our function, and let's put in our coefficient times 5 hours plus our intercept. And let's call out our score variable. And let's run this. And you see that if someone studies for 5 hours, they get a score of 51. An easier way to predict values is using the predict function. So mod.predict. And we have to use double brackets because it's passed as a 2D array. And let's put 5 in here. Let's call our variable. And you see we get the same answer. Now let's evaluate the model. And there's a lot of different metrics to evaluate the model. Because how do we know that we can trust those estimates? So that's why we split our data into 80-20. So we could make predictions with the test data and compare the values with the actual data. So let's create a variable called yPredict. And we want to predict our test data, which is the 80%. I mean the 20%. Let's run this. So now the yPredict variable, it contains all the predicted values for the input of the X test. And now we can create a data frame to compare the actual output values for the X test and the predicted values. So let's create a variable df.preds for the predictions, pd.dataframe. And we're gonna do this like a dictionary to create our data frame. And the first column will be the actual. and we want the y-test. Squeeze. Then we want the predicted column, and we want all our predicted value for x. Now let's call out our variable, and you see we get our actual values and our predicted values for the test data set. So here you can see we're off by like 1 or 2, 3 over here. We're off by a lot here. So evaluating the model, the metrics we use is mean absolute error. And what that means, it takes the difference from the actual and the predicted for all of the rows. It adds them up, and then it finds the average of those values, and that will be our mean absolute error. The mean squared error is similar, but it squares the absolute values of the errors. And the smaller the mean absolute error and the mean squared error, the smaller it is to 0, the better. The root mean error, it solves the interpretation problems with the mean squared error. Since the mean squared error is so large and it makes large errors larger, the root mean error is the square root of the mean squared error. And then the R2 score shows how well the data fit the model, and this ranges from 0 to 1. So now let's get some metrics from our model. So we have to import metrics. I want to import the mean absolute error, the mean error, and the R2 score. And then we want to import NumPy to get the root mean squared error. So NumPy as MP. Let's run this. So mean absolute error, I'm gonna set that to mean absolute error. And we're gonna pass in our y-test and our y predictions. Now let's do the mean squared error. Pass in our y-test, y predict. Now our root mean squared error. Then I'm gonna use our NumPy function to find the square root of our mean squared error. And next is the R2 score, and set that to R2 underscore score, and takes the arguments our y-test and y predict. Now let's print all of these at one time. So we're gonna print mean absolute error, and then let's round our mean absolute error, and we want to round it to 2 decimal places. Let me just copy this so don't have to and we put squared here, and we want to round the mean squared error. And then we want the root mean squared error. And we change this to our variable where we store the root mean squared error. this is the R2. And we want to put our R2 variable we made. And let's run this. Oh, it's np dot square root. And let's run this. And you see we have our values. We have our mean absolute error, mean squared error, root, mean squared error, and our R2 score. And like I said, the R2 score shows how well the data fit the model. And we see it fits the model by 97%. We get a root mean squared error of 4.35, which means that we are missing our values, making our predictions, and we're missing it by either minus 4.35 or plus 4.35. So now let's plot our actual and predicted data. So bear with me while I type this. Let's create the x-axis, and we want that to be the length of our y-test. plt.plot, plot our x-axis and our actual column that we created. And I want to create a marker, a dot marker, and we want to give it a label. Call it actual. And just copy this. Control C to copy, Control V to paste. And instead of the actual, I want the Y predicts. And I want to name it predicted. Then I want to show the legend. And I only want our plots to show and nothing else. So let's run this, see if there's any mistake. And there is. We misspelled actual. Let's run this again. And you see we plotted our actual and predicted. And you see the predicted line is pretty close to our actual values. So let's do one more exercise. Let's make a list of predictions.
Always with the scenarios.
I'm gonna import data frame. I'm gonna create a column called hours. And I'm gonna put a list of values that I want to predict. So I'm just gonna do 7, 7.5, 8, 8.5, and 9.5. Now let's create a data frame. Our data frame. Data frame, and we gonna call our hours that we stored our column in, and we want the columns to be hours. Now let's view our data frame. And now let's make a prediction of these values. I'm gonna set a variable called j dot predict our df. Let's call out j. And you see we get a list of our predictions. Let's put this in a column in a data frame side by side with each other. So I'm gonna create another column called list of predictions. And I'm going to put the values that's in our J variable. And let's call our data frame. And you see the hours, list of hours that we created. We put the scores, the predicted scores, right next to it. Now let's save this or export it to a CSV. So simply just call in our variable that has the data frame, and we use the .to CSV function, and in between brackets we'll put the name of what we want our CSV to be. So I'm gonna call it predicted_value.csv, and we're gonna use the index argument and set that to false because we don't want the index to be stored as a column in our CSV. And let's press Shift and Enter to run this. And if you look in the directory where you have this file, you should see your CSV. And you see here we have our predicted values, CSV. And here you have it. We exported our data frame to a CSV that has our list of hours and the predictions for the hours. Thanks for watching.
And it's got to be easier than when I was delivering pizzas. All right, push. Push. Come on. Come on. Almost there. Almost there. Just one more push. Here it is.